The room actually, I think my only connection to quantum marginals is mostly directly marginal to this community. Nevertheless, I was asked to chair this session, and so yeah, it's Nicolas Ressayre speaking on Eigencones and Levi movability.
Yes. Thanks to the organizer first, and I want to talk about some description of eigencones in the additive and if time is allow multiplicative case. Okay, I start this lecture on Blackboard by describing the so-called branching cones. So we consider the branching problem in representation theory. So to do this, we fix two groups. Which are connected, reductive, and complex. The main examples are GLN contained in GLN cross GLN over C. And the second main example for related to the quantum marginal problem is GL of some vector space V cross GL of another vector space W contained in GL of V tensor W. And we are interested in the branching problem for this inclusion. More precisely, we want to study the set denoted by LR GG hat, which is a set of pairs of irreducible representation of G and G hat, such that V is contained in V hat as a G module. Okay. This set seems.
Can you say a little bit about how this is connected to the quantum marginal problem?
See the first lecture. In the case when, in the second case, this question is equivalent to the non-vanishing of some Kronecker coefficients, which is equivalent up to homothétie to a spectral problem. Okay, for example, I will explain later because. We have this set seems to be abstract, but actually it is very concrete because we have a concrete parametrization of the representation, and to fix this I need to introduce some notation. The notation are very standard in representation theory of this kind of groups, but if you are not familiar with this notation, I write in blue the case of GLN. So I fix a maximal torus T, a Borel subgroup B, that is, I consider the set of diagonal matrices and the set of upper triangular matrices. And to this we can construct the set of characters of the torus, which is some lattice isomorphic to Z power R for some R called the rank of G. And in this lattice we have a convex cone, a cone. And the basic fact of representation theory is that this cone parameterizes bijectively the set of irreducible representation of the group G. In the case of GLN, here we find the set of partitions, more or less. Okay. But in general, we have such a bijective parametrization of the reducible representation by some collection of integers. So this set is actually a subset of some lattice, because it is a pair of irreducible representation. Each pair is represented by some object like that, and so you get a subset of some lattice. It is very concrete, and by a result by Briand and Knopp, this set has a structure. Precisely, it is finitely generated. It is stable by addition, essentially. Finitely generated monoid. And more or less, the question to decide between more and less is very interesting, but more or less, finitely generated monoid is a cone, a convex cone, that I denote like that. It is, by definition, the convex cone generated by this monoid. This cone, it is a convex polyhedral cone in some rational or real vector space, rational if you want. This one, it is a polyhedral convex cone, so something like that. Okay, and the question is to describe this set, this cone, by inequalities. It is the problem we are interested in. This result say there exist inequalities which allow to describe this cone, and the problem is to describe explicitly such inequalities. Now, the relation between the quantum marginal problem is that this cone has an interpretation in terms of eigenvalues of Hermitian matrices, and precisely this interpretation, this cone, this cone is equivalent to describe the description of this cone is equivalent to the description of the set of possible triples of spectrum of three matrices, Hermitian matrices A, B, A tensor B, in the case 2. In case 2. In terms of representation theory, it is equivalent to the non-vanishing of some stretched Kronecker coefficient, and in spectral on the spectral side, it is equivalent to the description of such a set of triples of matrices. Okay. In the first case, this cone describes the set. Maybe I have to explain this. In case 1, this is equivalent to describe the set of spectrum of three Hermitian matrices, or like that, of the form A, B, and A plus B, which is known as the Weil problem, and answered by the Horn conjecture. Okay, the relation is like that. Okay. Okay, now I want to state a complete description of this set, but I need to introduce a lot of notation to do it, and I am going to do it. Okay. We want to describe inequalities satisfied by points here. So I want to consider the dual of this space, which is actually the space of one parameter subgroup of the torus. It is also isomorphic to ZR and dual of the preceding ring in a natural way. Okay. My equations has to live in this set. I fix an element here, which has the following form for GLN. It is in blue, this is in GLN. Where is my blue chalk? My blue chalk is here. A one parameter subgroup is something like that. Is a map from the C star to the set of matrices, which has the following form: TA1, identity A1, TAS, identity AS. It is a map like that, and to this given, we have a lot of objects attached to tau. I want to describe these sets. First, I assume that A1 is bigger than 8S. This means that I look.
C'est les matrices. I don't understand. I cannot read the...
Identity of size I1, identity of size IS.
Okay.
Now I assume that the exponents are strictly decreasing. This means that I look at tau up to the action of the so-called Weil group, which is in the case of SLN, GLN, the symmetry groups acting on ZR by symmetry. The symmetry group SN in case of SLN. So up to action by of the symmetry group, I may assume that the exponents are decreasing. Sure. And now I want to consider all the objects. The first object is a subgroup of G. The subgroup of G in the blue case, in the SLN case, is a set of upper triangular matrices. I also need the centralizer of tau, which is in the blue case the set of diagonal matrices by block also. And I also need the center of the Levi of this group, which is called Levi. Okay, and now okay. Now I want to consider the homogeneous space associated to P of tau, which is actually
x times identity of I1. You have different x
here.
in the block.
It is any complex number times the identity of I1, etc. Any
numbers
star
in
is any.
blocks. Different numbers in different blocks.
The numbers of blocks and the size of blocks are fixed by tau.
But the scalar is
Are the same here.
But the scalar is the same in all blocks or no?
No,
And different.
different.
And the example you put in blue is the example for the marginal problem, or it's the other example for?
It is for the marginal problem because it is for GLN, and the marginal problem is GLN plus GLM in GLN times n.
So, so you have the marginal problem, but then you put them on the diagonal. And just
So this could be either G or G hat. This is a completely general way of saying now.
But the blue is the case of GLN.
In the two examples, the only groups which occur are GLN or GLN plus GLN, but it is the same situation by product.
Okay.
Okay. In the marginal problem, the group is GLN, so we can take this as a definition of P of tau, this as a definition of G tau, etc. Okay. It is for one GLN. It is for one GLN, where we have one GLN, one GLM, and a GLN times M. And for each block, each factor, it is this definition.
Is it possible to somehow use a different color than blue? Maybe
Blue is the case of GLN. Blue.
No. Use yellow chalk for GLN. If you use yellow, I think red.
Yellow is better than blue.
We understand paper, yes?
Yes, maybe green.
Blue is equal to yellow is equal to GLN case.
What's tau?
Right.
Tau is some one parameter subgroup like that. Is some map from C star to the set of matrices defined by this formula. And we have to think about tau as a linear form on the ambient space where the cone lie. The cone lie in some vector space, and I introduce this set as a set of linear form on this space. Because we are looking for linear inequalities, so we are interested in the set of linear forms. The set of linear forms are such subgroups. Yeah, there are different point of view on tau, but okay. Okay. Up to now it is hazy. Now we have G mod P lambda, which is, in the special case, a partial flag manifold. A partial flag manifold. It is okay. For example, a Grassmannian. For example, for the on case, a Grassmannian.
I2 greater than dot 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 greater than IS, not A1?
No. So no, that. Absolutely not.
So what
I have, using the action of the symmetric group, I can order only one thing, and I have to choose, and I order the exponent.
So there's a little confusion. Which is the partition? So that corresponds to what irreducible module?
Partition. The partition. I don't want
Do you want to use
to
fundamental weight?
answer your question because the partition more naturally parameterize the element of the dual. Here it is not a partition. You can because it is isomorphic, etc. But I prefer to say that it is not a partition. A partition is a point of this space. And here we have a linear form on this space. Tau is a linear form on this space. And your cone lie on this space. Well, to be more precise, you have to put tensor Q and you have to put the two groups. And now we are interested on we fix a linear form on this space, on this kind of space, to make notation more comprehensive. I forget this part, but it is the same nature. It is this one, if you want. It is the same nature for the group product. And I want to explain a list of things associated to linear form on this space. And associated to a linear form like that, we have a parabolic subgroup, an homogeneous space, which is a flag manifold.
Question. Is tau determining a subset of the simple root, so you just have the parabolic, or is it also determining a module that you want G mod P to be embedded in?
The set of roots.
The set of roots.
If you want, but I don't want to think about this. But if you want to think about tau as selecting some roots, tau is a linear form on the set here. The root lie here, and so you have the sign of tau applied to the set, which select positive, negative, zero roots, and all these things can be expressed in terms of positive, zero, negative roots. Okay. Okay. Now it is complicated, but you have a decomposition of this flag manifold parameterized by some quotient of this group. This quotient is precisely Sn times I1 times SIS. And the point is that this set has the cellular decomposition indexed by this set. For the case of the Grassmannian, it is a decomposition called reduced echelon, I don't know in English, matrice échelonnée réduite in French. G mod P lambda is the union of B orbits and the B orbits are indexed by this set, by this quotient group. This decomposition is very sympathetic to understand the topology of this space because it is a cellular decomposition. Each orbit is isomorphic to some vector space. And the dimension of this vector space is called the length of W and is by definition the set of positive roots which are sent to negative roots. Okay. Where in X star of T I have two sets defined by a root. It is standard. I have some okay. Given with the group, we have a root system for say a particular set. Okay, we are almost ready to state the cardinality of
the set. You define
oh yes, thank you. The cardinality of this set. Exactly. Check. Okay, I want to. Can I switch to the projector, please? Thank you. I want to finish the description here. Okay. I explain that this decomposition gives a description. Okay. This decomposition allows to understand the cohomology of this space. More precisely, it allows to define a natural basis, once this decomposition is fixed, of the cohomology group or cohomology ring of this space. Okay, it is the base, called the Schubert basis. Okay, now we don't have one group but two groups, and so tau, which is a map from C star to T, is also a map from C star to C star to T hat, and we have define all these objects. The two constructions for the small group and the big group are related by the following map, by an inclusion between this homogeneous space in this one. By construction, this space is contained in this one. In the first case, where the small group is GLN and the big one is GLN plus GLN, this is the diagonal inclusion of some Grassmannian in the product of two Grassmannians. It is this map. And this map induces one in cohomology by restriction. I almost can state the description of the cone LR of GG hat. Okay, you can forget the first sentence. It's just yes, you can forget it. A dominant weight belongs to the cone if and only if some linear inequalities are satisfied. Oh, lambda I is tau. Okay, we have tau applied to a character. Tau is a linear form on the set of characters, etc. For the small group and for the big group. Now, what are this set of inequalities is parameterized by a set of tau, a set of W, a set of W hat. What are the conditions? Yeah, lambda I equals to tau. Sorry, mistake. Lambda I is equal to tau. Sorry. And so I have to to explain the parameterization. The parameterization, you have to take a dominant one parameter subgroup. This means that the sequence is like that. Dominant just means this. It is not important. It is I look the equation up to the action of W. Okay. Indivisible, it is just indivisible in the lattice. It is a point on some lattice, and it is indivisible like that. I have to explain adapt. Tau is adapted if the set this is an hyperplane. It is a linear form on a vector space. We have an associated hyperplane like that. And I ask that this hyperplane is spanned by some weights of T acting on the quotient of the Lie algebra G hat modulo G. Okay. We consider the action of T on this set. So it is, the action is given by more or less the set of collection of the roots for big groups, restricting to T. You get a collection of points in some vector space, which is this vector space, and you select the hyperplane spanned by some subset of this given set. Okay. To describe the set of adapted one parameter subgroup, you just have to do this. Okay. For example, if the set is in dimension 2, it is obvious. The set of hyperplane generated by a collection of points is just a set of lines like that. It is adapted. Okay. Now the next condition is the condition in cohomology using this morphism. It is a complicated condition to understand in particular.
Is not a consequence of what?
No. To be precise, the condition which is the fact that the sum A over all chi is equal to the sum A over all chi is a consequence is a consequence of 1. But okay, it is a degree condition. Okay, now I have to explain what is this condition. This condition is can be understood as a condition of multi-degree. I consider this set, which is the set I explain in yellow. It is the set of position of entries of matrix. Okay? It is this set of position. It is a subset of the set of roots of the group. In the case of JLN, the set of roots is, by definition, more or less, up to the diagonal, the set of position of the entries of the matrix. Now, I consider this, it is a subset of phi. It contains my set phi of W. Now, I want to explain what is this chi. I just
What's phi of W again?
what phi of W is this. You are right. This set without the cardinality, the set of inversion. Okay.
Did you want W alpha in phi minus or kept in phi plus?
Minus W of alpha.
Minus W alpha.
Just to-
See that minus sign. Okay, then it's logically consistent. Good.
Okay.
Non-traditional, but
Yes, I have this set of position, and I assert that this set of position is naturally partitioned in parts. In this case, any children could explain that this yellow zone region is the reunion of three rectangles. 1, 2, and 3. Now, in general, we have such a partition of this set as a union over all the characters of Z. I don't explain because it is of this set. In the particular case of JLN for this parabolic subgroup, it is just the partition of this region in three rectangles. To be more technical, it is you consider an element here is a character of T. You restrict it to Z, and if the restriction is chi, you put this root in this set.
okay, and then what's phi of W chi?
Oh, I explain now. Okay, this is this one, and phi of W is a subset of this set, which is partitioned. And so it is also partitioned. So this is simply the intersection of phi of W by phi of U mod P. No. This is this one. Okay. My set of roots is naturally partitioned, and I partition all this set of inversion according to this partition. And I ask that the degree condition, because it is a degree condition, has to be satisfied for each block. The Michel Verne remark is that that 1 implies that the sum over key of this is equal to this one. Okay. Condition 2 with the sum is a consequence of condition 1, so it's unuseful. But without the sum, it is stronger, sure. And so it is a non-trivial condition. Okay. It is the statement. This statement is, in some sense, it is optimal in some sense because we have the minimal list of inequalities. So, but it is actually difficult to apply it concretely. Each given, except each condition, excepted the last one, is difficult to check. The first condition to be adapted could be actually very complicated. For example, a computer is able to compute the set of adapted one-parameter subgroup in the case of GLN cross GLN in GLN square. If you are not so clever, if you are a computer to describe the set of adapted element of, so the set of hyperplane, just a set of hyperplane for the case which are in, for this case we ask to a computer what are the collection of hyperplane generated by some subset of this family. You can your computer answer if n is smaller than 3, and if n is equal to card, it is already very hard. So it is a difficult question to apply concretely this statement, but okay, maybe it is the nature and not the statement, because the statement gives a minimal list of inequalities. So we need these inequalities. Any statement gives it, and so it is actually difficult.
Suppose you were only interested in dominant weights new hat, which are very degenerate. Could you do better? Like not of, you only vary the new, but not new hat.
You fix new hat?
I fix new hat for.
Oh, it is no. It is worse. Because you have a symmetry, you have a beauty, and you take a beautiful polytope as a cube and intersect by an hyperplane. You can get a square, an hexagon, a triangle. It is complicated to understand, but yes, the whole polytope is more beautiful than a section taken randomly. Now, I think it is not a good strategy. And I think, I'm not sure, it is not a proof. Okay. To break symmetry is not a good idea, I think. Okay, it is difficult in practice. The last condition is very easy. The last condition is combinatorial and very easy. You have to count roots, and this condition is good. The second condition, I will speak about it later, is complicated. Okay. It is difficult, but we can apply, and we can find some results. And I want to state one, which is an inequality for the quantum marginal problem, or a collection of inequalities for the quantum marginal problem. So, I take 3 partitions of the same integer n, satisfying some condition about the length. Bon. So, and I assume that the Kronecker coefficient is non-zero. So I assume that alpha, beta, gamma belongs to some cone as defined before. And the consequence is that this set of partition, alpha, beta, gamma, satisfy some this family of inequalities. The condition 2 is an inequality linear in the entries of alpha, beta, gamma. I just have to explain what is alpha I. This is simply the sum over the index given by I. I is a subset of indexes of cardinal R in okay. It is alpha I plus 1. So we have sum and differences of elements like that for some partitions. If you know the Horn inequalities, it is very similar to the Horn inequalities. Some partial sum of the eigenvalues has to satisfy inequality. It is such such a form. And what is the condition which to have this inequality? This condition is some Littlewood Richardson coefficient has to be equal to 1. Also, if you know the Horn case, you know that it is exactly this kind of condition which parameterize the minimal set of inequalities in the Horn case or Weil case. Okay, so actually this statement is an extension of the Horn inequalities. Extension of Horn inequalities, not really Horn, minimal Horn. Of minimal Horn inequalities, if you know, from LR coefficient to Kronecker coefficient. Okay. Actually, it is true that Littlewood-Richardson coefficients are some particular Kronecker coefficients. It is a Littlewood-Murnaghan statement.
What are the taus? What is tau k, tau l, tau j?
It is the usual transformation starting from a subset to a partition. It is. I just want to understand that this is some Littlewood-Richardson coefficients associated to I, j, k is equal to 1, and this some coefficient, some Littlewood-Richardson
I
coefficient.
think your theorem changes notation mid statement.
Why? Okay. This is a cohomological condition depending on I, j, and k. For any AG key such that you have this condition, you have this inequality. No? It is a collection of inequalities satisfied.
What is S of RE again?
The set of subsets of cardinality R of the set 1, 8. It is a subset of indexes. Yes. If you want to understand the statement without precision, it is a family of inequalities satisfied by the Kronecker cone, parameterized by the condition some Littlewood-Richardson coefficient is equal to 1. And the precise statement is this one, but it is not very. It is not the moment to understand maybe. Okay.
Littlewood-Richardson coefficients are associated to the reduced alpha, beta, and gamma. Is that
No.
because
No. Really, in this statement, this coefficient, the Kronecker coefficient is a representation theory coefficient, is a dimension of invariant section, is a multiplicity in some representation, and this coefficient is not a multiplicity. It is a cohomological condition in the cohomology of the Grassmannian. But you know that the cohomology of the Grassmannian is encoded by the same family of integrals than the tensor product. But it is a.
Would it be possible to give an example?
Yeah.
Yeah. Just for like concrete alpha, beta, gamma that are non-trivial.
A concrete alpha beta gamma which is non-trivial.
Can we just go through it and see what comes out?
I don't. No, I'm not able to do this.
For instance, if a different example, if I and j and k were empty that you don't look at now. Maybe
No,
maybe
it's,
exclude this.
no, you're handed the alpha, beta, gamma, theta.
Yeah, no, I know. I want to just exhibit
Like
one
alpha, beta,
specific
gamma,
inequality that I
rectangles.
have in mind.
Oh, you are right. In the case where I, G, K are empty, you find that n minus alpha 1 minus beta 1 is greater than minus gamma 1, which is called the Littlewood-Monaghan inequality. And it is true. It is an inequality satisfied up to the condition Kronecker is non-zero. Maybe the most famous one.
There's a similar inequality for this marginal problem, which, I mean, of course looks the same.
Yes. Actually, it is really the case which is interesting is maybe I want to speak about this point just. If the Monaghan Littlewood-Richardson inequalities is an equality, if you are on the boundary of the polytope, this inequality belongs become equivalent to this one. And if you know, this is exactly one Horn inequality. Some partial sum of elements of parts of alpha plus some partial sum of beta is greater than the equivalent notion for gamma. It is exactly an Horn inequality. Maybe it's an example. And this condition, it is the usual condition to parameterize the Horn inequality. So this statement is precisely an extension of the Horn inequalities in the statement of Kronecker. It is what I mean. Yeah. Okay. I wanted to no.
The cohomological condition
Yes.
it's not obvious that it's equal to the Kronecker condition. So
No, the cohomological condition
why
in
is
this
now the Kronecker
statement,
coming in?
the cohomological condition in this statement, this condition is in the case of this statement, this condition.
But how do I
Okay,
know?
I have to switch between the two statements. The non-vanishing of the Kronecker coefficient is equivalent to some point belongs to the cone. Okay, and the cohomological condition in this statement is this one. Yes, very. It is an example of. It is not an if and only if here. No, absolutely not. It's just an example of inequalities you can obtain. But to describe the set of inequalities, I explained that it is very complicated, combinatorially and topologically. Yes, not only combinatorially, but to understand the cohomological condition is really complicated. Okay, I wanted. Okay, I forget this part. I drop one part of my talk, which is the second part of the title. I will not speak about Levi movability, but I want to talk about the multiplicative equivalent to Horn problem. Multiplicative Horn problem. Okay. For the you I take a compact Lie group connected and I take inside three conjugacy classes. And I ask the following question: is it true that you can obtain the identity matrix by making the product of an element of O1, an element of O2, and an element of O3? If you know, the on problem is the same statement with a plus, and here coadjuvant orbits. So it is the equivalent question, multiplicative question. Okay. It is known that this question can be answered by describing some polyhedral cone or polyhedral polytope, if you want. More precisely, the set of conjugacy classes of K in K is in bijection with that I call A star, which is the set of one parameter subgroups times R. Oh, G is equal to the complexified group KC. K is UN and G is GLN. Okay, such out tau is K mod K, but for the adjoint action.
Oh, okay.
So it is a non-trivial object.
K mod at K. Yeah.
Precisely, it is a polytope. And this polytope is the fundamental alcove in the set of one parameter subgroups. And the fundamental alcove is like that. It is a simplex, actually. It is a simplex. Okay. So, since we can understand the set of orbits as a polytope,
May I try to rephrase this question in layman's language, just to check whether I understand? So does it is old? So I have like three spectra. Like I think of the unitary group.
yes,
And the question is: are the matrices A, B, C of the prescribed spectra such that A times B times C equals unit matrix?
exactly.
You are inquiring about the condition about these spectra.
Yes, exactly.
But my
And the spectra is the spectrum is a set of points on the unit circle, and you can think about it as a point in the interval 0 to p, and so it is this one.
unitary. I said
This polytope. And the relation between this polytope and the matrices is also the exponential of theta. See Bourbaki or the reference. Okay. Now the set delta K, which is the set of triples. What is the notation here? To 1, to 2, to 3. The set of triples in the alcove such that the associated orbits satisfied your condition. This set and the question here is equivalent to a description of this set. Now this set is by a result by Eigencones and Woodward a convex polytope. It is Eigencones and Woodward, I think, is a polytope. And the question is the same as before. What are the inequalities which parameterize, which characterize this polytope? Here it is an answer. I take a point in my ambient space, in my product of three polytopes here, and I ask for this point belongs to delta of K. So I have a triple of spectrum, and I ask if you can get the identity matrix by making a product of three matrices with this prescript spectrum. The answer is yes, if and only if some linear inequalities or affine inequalities, to be more precise, some affine inequalities are satisfied. These inequalities are parameterized by what? They are parameterized by a simple root, which is given with the group, and a triple of Schubert classes W1, W2, W3, similar to W, W hat, such that the condition 4 is satisfied and the condition 5 is satisfied. If you compare with the preceding statement, yes, I will explain later. It is very, very similar. Okay, this is the same. The inequality is more or less the same, fine linear, and it is the same. The main difference here we have a cohomological condition, and here we have this strange or not so strange condition: GW is equal to 1. GW W1, W2, W3, D is the Gromov-Witten invariant of degree D in G mod P of beta. P of beta is a maximal parabolic subgroup associated to the simple root beta, with the notation of it is if you want omega beta change to be compatible with the notation P of tau. But okay, it is the maximal parabolic subgroup associated to beta. This invariant is more or less the set of the cardinality of the set of curves from P1 to G of P of beta of degree D by my three Schubert classes. To be precise, you have to put these three classes in general position to get a finite number, and this finite number is this Gromov-Witten invariant. It is the structure coefficient of the so-called quantum cohomology of the homogeneous space. Okay. It is this condition. It is a cohomological condition, but in the quantum cohomology, not in the ordinary cohomology. It is the condition 4. And the condition 4 is completely analogous to the condition above.
I suppose you don't go to all the non-integer beings, some, just a few of them?
It is finite. No, actually not, because as you know, the product of two Schubert classes is a finite expansion. It is a priori, the quantum cohomology is polynomial and not formal series. Okay, the product of two Schubert classes is a polynomial. Is polynomial in Q, in the variable Q. You have a finite expansion. No, actually.
To me, it's like a finite number of inequalities. That's all what I am worried about.
Because when you fix W1 and W2, the number of pairs W3D, possible pairs W3D is finite. Okay? When you fix two. Okay, it is finite. Actually, the statement without condition 5 is due to Telemann and Woodward. And I add the condition 5. I want now to compare the statement without 5 and with 5 by explicit computation in these cases. Okay, you have the group on the left side. You have the number of inequalities given by the theorem. Okay, so the number of inequalities given by the theorem. And here we have the number of inequalities given by the Telemann-Woodward statement. Okay, I have to. Here it is an intermediate Eugene Belkade-Kumar statement. Okay. Okay. intermediate. You see in the big case we have a factor 10 between the two statements.
Is that the non-redundant one, or you don't know?
Oh,
Do they are the minimal or no? You don't know.
I will say in 1 minute.
Okay.
On this case, it is minimal. It is a result of computation by the software normalize. Okay, it is minimal in each case. Here, my computer is still computing. Now, today, on the archive, there is a paper by Belcalé and Kumar, which asserts that in these two columns, you have equality. So, Belcalé Kumar just post on the archive this statement, more or less, different formulation, but an equivalent statement. So we get independently this statement, but then obtain the stronger result that this list of inequalities is optimal. Okay. So here we can make, the name is my independently Belcalé and Kumar, and Belcalé and Kumar moreover prove that the two columns here are equal. So it is not useful to wait for my computer.
Well, we know the answer now.
Maybe for this column.
You go faster than your computer.
Okay, thanks.
Yeah.
Thanks.
Okay. Any more questions? Oh, yes.
Question coming back to the quantum marginal problems.
Yeah.
So you showed this theorem with the inequalities. Very
This or this one?
No, previous.
Yes.
This one. Now we specialize to, I think it was case 2. Case 2, okay?
Okay, any question?
No, case 2. So we have.
Yes, case 2, okay.
Now we have this paper with Matthias where we studied the cone from Kronecker coefficient. It's actually a slice that 2 of the 3 partitions are uniform, all of the same size, uniform distribution. And then we found there is no condition at all. Now I wonder, can you see this from your theorem? I mean, it should be a consequence of the theorem, but this looks terribly complicated to me. So.
No, but the method used to prove this statement, actually the more general statement is for a reductive group acting on a projective variety, and the cone is a set of line bundles such that there exists invariant section for some power. We have general result on this set, and I think that different non-zero. I don't assert that any result is easy, but it is the direction. How can I explain this?
I mean, the meaning is that if you have any, in this specific situation, you take any spectrum and then uniform spectrum, and it must satisfy all these inequalities.
Yes, but
Because there cannot be any condition. So
it is possible to, because actually we have this big polytope, and you intersect this polytope with a very degenerated boundary of the dominant cone, and the assertion is that this intersection is full.
yeah, the question is whether it can be seen from there.
And I mean that if you want to understand this intersection, actually it is not this statement that you have to use. You have to use the action of the group, the UN square, on a more degenerated variety, a partial flag manifold, not the whole flag manifold. Yes, this statement is a statement about the action of the group G on the flag manifold G mod B close G hat mod B hat. And if you want to look at degenerated non-regular weights, we have to consider the action of the group G on partial flag manifolds. And maybe the general result in this general context applied to partial flag manifolds could give this kind of statement.
But no easy proof inside, no easy other proof so far. Maybe.
No.
We can have one more.
Yes. Could you just quickly give some intuition, although I guess it's in Telemann and Woodward, for why Gromov-Witten invariance would suddenly appear? Is this at all generalizable? Is this magic to this case?
Yes, it is. It is a long story. The one bridge is the notion of semi-stability of parabolic principal bundles. And the notion of parabolic principal bundle is more or less clearly related to Gromov-Witten invariant, and is also related to this kind of spectral problem by multiplicative version of infinite dimensional version of what are the name? Between symplectic geometry, the relation between the symplectic reduction and GIT quotient. Yeah, the ingredients, the keywords are symplectic reduction, GIT, and parabolic bundles. Okay. And you have to put a long story with these keywords to get the equivalence. It's not obvious at all.
Well, I think let's close the session, so thanks.